Okay, so we're going to start looking at, doing an actual design problem, determining the minimum shaft diameters on a shaft. Okay, it's a pretty big process, as I've been kind of alluding to. Hopefully, you got a chance to read through the two examples that we're going to be doing to kind of get yourself, in the mode of what the process is going to be. But we will deviate somewhat in some places, and I'll go through all of that with you. We have those two main examples to go through this shaft design procedure 2 times. Both shaft design procedures are part of your practice problems. So if we take a peek at our practice problems here, there's just these 2 examples, okay? So I'll let you know what is part of, if you would, the deliverables and what to hand in to get full credit, which is going to mimic then as well the 2 homework assignments that you have that are going to be the kind of full shaft design. So we'll be talking more in detail about that. Always remember, there's a couple questions here at the end that I would like you to answer, again, in your own words. This doesn't involve, a big essay or doing any research. It's just, really kind of how are you feeling about the materials and maybe some other, similar types of questions. So there's our practice problem, and it's going to be these 2 examples. If I go back a level, in the learning plan, okay, let's look in the learning plan. We started going through the PowerPoint presentation already, all right? So we've kind of gone through kind of the basics, all right? We'll do a little bit of a review and kind of, reference some things before we jump in, but for the most part, content-wise, we've got quite a bit under our belt. Up here is that MD solids. We're going to use this to aid us in creating the shear and moment diagrams. Okay, so we'll do a demonstration on how to use that when we get there. All right, and it's very, very easy, quite honestly. So and that's why I love it. It's a great little program. Then you'll notice down here when we perform our example problems, we will be using this. This is the procedure handout. Okay, so up in the front here, we've got the copies. Otherwise, the PDF version is right there, and this is going to give us step by step how we're going to proceed through. And then here is our shaft design Excel spreadsheet. So I encourage you to download that right now. I have made some changes as of last night. So if you downloaded it before late last night, then we're going to want to download again and get the most current version. Okay, because there are some things that I improved. Not that anything was bad, but I found a couple things that I thought would make it easier to use. And then you'll notice down here, submitting the practice problems, as well as assignment number 6 then is going to fulfill the requirements for this module. Okay, so what I want to do is I want to look at MD solids first. No. We're going to go into the PowerPoint. Sorry. I want to kind of finish up the PowerPoint a little bit and refresh ourselves on where we're at. So as you know, we kind of made it all the way through until right before the practice problems. And so I have what I want to do is I want to talk about what we're going to be using to determine these minimum shaft diameters. Now, the minimum shaft diameters are going to be determined by the types of conditions that are going to create the stresses that we have to use then equations to determine minimum shaft diameters. Okay, so the main types of stresses that we're going to be encountering are going to be vertical shear stress, torsional stress, bending stress, and then in combination, bending and torsion. Okay, and so our job as we lead up to determining the minimum shaft diameters, and there's work we have to do before we get there, is really to be able to pinpoint at which sections along the shaft do these either occur by themselves or in combination. Okay, and that's going to be our job before we get there. So so the process that we're going to be going through is going to be, preparing us for that. Now, the equations for each one of these are found on the pages that we see here. So we might as well take a look. So on page 519, at the top of the second column is going to be the vertical shear stress. So I'm going to go underneath here. And that equation is right here. So it's not a tough equation. All right. So the minimum shaft diameter, capital T, is going to be equal to the square root of 2.94 times KT. KT is going to be whatever stress concentration value is the largest for that section, that part of the shaft that you're trying to calculate. Capital V is going to be the shearing stress. Capital N is going to be the like the safety factor or design factor. And then your S sub N is going to be what we call the endurance strength. We'll be calculating that as part of our inputs, okay? So not a hard calculation. Doing it by hand wouldn't be that difficult, but when we look on our spreadsheet, we're going to see that in the vertical shear section only, this is going to be the equation that's there, okay? Now, the other types of stresses that we see, the equation is going to be found on page 521. And the base equation here is 1224. 1224. Now, 1224 combines together in one equation for a minimum shaft diameter, bending and torsion. Now, the bending part is right here. It has to do with the moment internally to that shaft that's created, okay? And then the second part of that equation is going to be the torque part. So if I am in a bending only situation, I am just going to eliminate this portion of the equation that has to do with torque. If I'm in a torque only situation, then I'm just going to get rid of, if you would, or take out the portion that is due to bending. When I have bending and torque at the same time, then I keep it as a complete equation. So if you look in, and we'll look at the spreadsheet in a little bit, you'll notice that those equations are kind of split out into the different sections. Now, this one is a little bit heavier lifting, okay? Takes a little bit more time to get through, but still not terribly complicated, but having the spreadsheet definitely makes it a little bit easier, okay? So here you're going to notice a number of variables that we've talked about as well. So N is going to be that design factor. It's always 2 unless otherwise specified, kind of for normal industrial cases. KT is going to be whatever stress concentration factor is the largest or present for that critical section. M is going to be the resultant moment, internal bending moment that's at that portion on the shaft, okay? We'll talk about what that means when I say resultant. Endurance strength, okay? Again, this is going to be a function of the material that we pick. Capital T is going to be the torque that's present at that section, and then SY is going to be the yield strength of the material, okay? So there won't be any manual calculations that you have to do, but in case, for instance, let's say you have the spreadsheet and you're kind of looking at it and wondering how it's working, you're going to, go on that section, you're going to notice it's a pretty long string for the equation. But if you wanted to make any additions, or if you wanted to copy someplace, here's your base equation that you can certainly that you can certainly play with, okay? So those are going to be the stresses that we're going to see. And again, our job before we even get to the spreadsheet is to know when is it going to be appropriate to use either by themselves or combined. Okay, and we'll talk about that and see that. Now, as we prepare to start our shaft design, you need to know some things. And we're going to be given these as part of the problem statement here in the example problems and in the problems that you're going to do for homework. But when we get to our gearbox design, okay, like getting that process started, we're going to have to do some of this work up front, okay? Because in that case, you're just going to be given some specifications, and now it's like, hey, there you go. So some things that we have to know in order to get to the shaft itself, we have to, number one, know what are the machine elements that are going to be on our shaft. What are we using here? So gears, belts, chains, those are the things that we've been looking at in machine elements leading up to this. The next thing we need to know are types of bearings that we're anticipating using. We won't know exactly what they are at this point, but what type of bearings. For the types of elements that we're going to be looking at here, we're going to just use regular radial bearings. If there would be any side loading, like if we had worm gears or helical gears or bevel gears, then we would have to look at different types of bearings, but we're going to keep it radial loads only. So we're going to keep it belts, gears, and chains. So we need to know our bearing supports. We also need to know what are the dimensions on center for each one of these. Okay, so I won't know how thick that bearing is because I'm going to need the shaft design to actually size it. Okay, but I'll know on center where it's going to be. Okay, so center lines of the centers of the face widths of gears, the center lines of the face widths of belts, the shivs, the sprockets for the chains, and then also for your bearing supports. Okay, bearing supports. We're also going to have an idea of how we're going to locate these elements. Are we going to be pushing up against a shoulder on one side and then retaining ring on the other so that it doesn't, walk off the shaft? So I've got to know where those types of elements are as well. And that's kind of like the conceptual design that you do at the beginning. And we're, like I said, for the problems we do in this chapter, example problems, that's going to be given to us. They're going to already have a scheme that's going to happen. And we not only have to take into consideration, how to locate it, but also how to assemble it. It happens, you're designing, and all of a sudden you realize, crap, I kind of, boxed my gear in the middle of my shaft, and now there's no way to get it on and off. Well, then you gotta go back and you gotta fix that. Okay. So always be thinking about assembly, and then even if I had to repair this, what's going to be the easiest way to pull that apart as well. Okay. So always be thinking about that. So when we talk about location elements, those shoulders, sharp, well-rounded, we talked about the KT factors that have to do with those. That's why we have to know these now. And then also any torque and rotational transmitting keys. So are they going to be the profile key, or are they going to be like a sled runner key? Because KT values are different associated with those as well. So these are the things concept-wise that we kind of have to know about our design, spatially, physically, size-wise, how we're going to put this together in order to get started on shaft design. Okay. If we don't know these, there's going to be a point in the shaft design, we've got to figure that out. Okay. But this sheet right here, this slide right here, like I said, these are going to be given to us in our problems you're doing in our chapter. But in gear design, those are things as a designer, you get to kind of, figure that out. Okay. All right, so design example 12.1, okay, 12.1. So we are going to be looking at designing a shaft, and it has to do with the figure found at the beginning of the chapter where they kind of had, we've been referencing this, at times. And also on pages 511 is where I'm sorry, 521 is where I think the example here is 511, 521. But if we go a little bit further on my spreadsheet here is the overall scheme that we have right now for our shaft. This is how we envision putting this together. So let's walk through what's going on. So the center line of the shaft all the way down, notice that they have identified points A, B, C, and D along the length of the shaft going left to right. This is going to be each one of your critical sections. At each one of those sections, we need to determine what is the minimum shaft diameter. Okay. So at A, we picked that as a critical section because there's a gear mounted there. My next critical section is B. That's where we have a bearing mounted. Then the next one is going to be C, gear, and then we have another bearing at D. So anywhere there's something going on, all right? And whenever there's something going on, you'll notice that there's shoulders, keys, and retaining rings that are there. And those are the things, or those are the places where we're going to have stress concentrations that are going to pop up on us. And that's what we're designing for, like where it's going to break. Okay, what is our worst case scenario? We're not going to necessarily worry about, diameter 4 here, because that's got, that's in the middle. There's really nothing going on. I mean, yeah, it has some distance it's going to cross, and yeah, it's got to do a little bit in shear and moment, but nothing like what's going on at A, B, C, and D. Okay, A, B, C, and D. You'll also notice here, the other things that we talked about having to know before we get started. You'll notice that there are keys in place here. There are shoulders. There are also the retaining rings. Okay, how these things are going to stay on. Let's talk about each one of those. Now, at the gear, you'll notice right now we've got, I'm going to try to zoom in here a little bit so it's a little easier to see. At the gear, you're going to notice that we have a key, all right? That key is there so that we can transmit the rotational speed as well as the torque, right? So that has to be there. The next thing that we have is we have on the left-hand side, we've got a retaining ring, all right? We have to have that identified and known. And then on the right-hand side, we've got a shoulder. So to locate this so that this doesn't move around, we're going to push it up against that shoulder. And on the other side, we're going to put a retaining ring. Now, by theory, if you would, this is a spur gear. So it's only going to have radial loads, meaning they're all directed perpendicular to the center line of that shaft. That's that radial and tangential load that we've been referring to. Theoretically, it should not walk off the shaft if everything is, perfectly aligned and all the forces are, acting the way they're supposed to. And as you know, when we put things together, there are going to be imperfections, there are going to be tolerances, and things aren't going to be perfect. So we have to have a means of keeping it on the shaft, and that's what the retaining ring is doing on the other side, okay? Now, that radius there, that shoulder, when we have that shoulder there, there's going to be a radius that we can create. Now, in the case of the radius, when we have an element that, if you would, we have control over, we're gonna bore out that gear and we're gonna put a chamfer on the front of it to lead in. Because of that, we can make a nice, well-rounded radius that's gonna fit with that. So when we look at our KT factors, for instance, on page 517, we have two different radiuses. We've got well-rounded. So here would be like, a zoom in, and we would have a chamfer, and then we would be able to create a nice generous radius there. KT factor associated with this is only 1.5. But if I am mounting a bearing, I don't have control over that radius. That I have to live with. And we know that a bearing is going to have a really tiny little radius here. So that means that my radius has to be even smaller than that, so that it seats up on the actual shoulder itself. Okay. Well, with that, that means that I've got to make a really tiny little radius. So now my KT factor went up to 2.5. Okay. So knowing where these bearings are and on what side I'm shouldering is essential. And that's at this place before we even start worrying about the diameters. So if we go back over here on the right-hand side, I've got this sharp corner. On the left-hand side, I've got a well-rounded radius, and that well-rounded radius is so that I don't, because the bore in here, that bearing is being pressed on that bore. We don't want to press the entire length to get it to its shoulder. So you'll notice that we turn this down, we put a well-rounded radius in front of it, and then the length is just a little bit wider than whatever that bearing would be the pressed portion, but then we locate over on the right-hand side with that sharp radius. Okay, so different conditions as we look on this from left to right. Do you see that? One side is going to be the sharp corner, the other side is going to be the well-rounded radius. All right, and our KT factor is going to change then. Then as we move further and further to the right, you'll notice here that we come upon our next gear. Now this gear, you'll notice that the largest diameter 4, is right in the middle. So we're assembling our bearing at B and our gear at A from the left-hand side. And then we're assembling the gear at C and the bearing at D from the right-hand side. Okay. So again, kind of thinking about the assembly process. Here on the left-hand side, because we can control the chamfer of this, and it's an element that we can bore out and put that chamfer, we can put a nice radius in there. We would have a well-rounded radius on the left-hand side. We would have a profile key going through both sides, but then on the right-hand side, to keep it from walking off the shaft, we need a retaining ring. So the retaining ring groove is there. Okay. So again, left side, right side, two different conditions because of stress concentration values. Right. And then the last thing that we have on the right-hand side at D here is going to be our bearing. Notice that on that left-hand side, that's going to be the side where it's going to be, shouldered so it can locate. So again, KT factor associated with the sharp corner there. So this is going to be the arrangement of the shaft that we'll be using and referencing back to for the entire process. So any questions right now? So you also notice dimensions here between the centers. These are all the things that have to be in place, or at least you don't have to have them sized, just like this is how we're going to mount that shaft. And these are the dimensions that we're going to use. We need all of this in place. Okay. So if it's not given to you, or you're the designer and you have the control over that, then you need to have those things in place. I'm going to go back over here. So our design of our shaft says, and this is going to be starting on page 521. The problem description says we're using the material SAE 1144 oil quenched and tempered 1000 steel. That's just kind of a run-of-the-mill good shaft material, but you can really use whatever you want. Okay. We'll notice that the next example we uses a different type of steel. So then we just have to gather the information we need on the spreadsheet. So it says that the shaft rotates at 600 RPMs. We have 200 horsepower coming in on A, I believe, and it's leaving on C. Okay, we'll see that in just a little bit. And we want to determine the minimum shaft diameters at each one of those critical points that we just looked at in detail, A through D. Okay, A through D. So that's our job at the very end. Okay, so let's get our spreadsheet out. So I'm going to go back to learning plan number 6 or module number 6 learning plan. And you can go ahead and you can download, if you haven't already, the most recent shaft design. Now, to be sure you have the correct one, just make sure you have these little yellow highlighted areas on sheet 2. On sheet 2. Okay. And then we're actually going to start on sheet 1. I must have saved it when sheet 2 was open. And if you don't mind, I didn't clean this up. I'm going to get rid of all my blues. I'm so sorry. Oh my goodness. That's okay. That's all right. So anything that's in blue down the middle here, I apologize. Sorry. I thought I had intended to. I guess I didn't. All right, so we're going to start on sheet 1. We're going to start on sheet 1. I want to peruse this first before we really start using it. Our sheet 1 is going to be our inputs. If you want to change the sheet title at the bottom, you certainly may. And if you want to change it in any way, that's totally fine. This spreadsheet is going to look like the ones that we have been using, up until this point for, the keys, the bearings and the gears and the V-belts and the chains. Okay, so same process, same kind of look. So we're going to be using this middle column down the middle, and anywhere there's something in blue, you need to input something. And then there's notes on the right-hand side pertaining to units that you would need to have it in, as well as where it will be found. So depending on if you're in the 5th edition or the 6th edition, I think most everybody's in the 6th at this point. I have the references there for you. Okay, so material at the top here. Then as we go down, you're going to notice that there's some places to input torques. Okay, so it's going to calculate the torque for us. Torque isn't a hard equation, but as long as we're here, we have it. And then you're going to notice that we have gear forces, and we have chain sprocket forces, and we have V-belt sheave forces. V-belt sheave forces. Okay, so we're going to be actually seeing how this works. The first example we're going to do is just going to be gears. And then the second example we're going to do is going to incorporate both chains and sheaves as well. Okay, now that's kind of the input sheet number 1, the initial information that we're going to be needing. Then we're going to go to sheet number 2. Okay, so I'm going to go all the way up to the top here. Sheet number 2, as we go all the way up to the top, you're going to see that these maroon sections are like the main headings. And in each one of these sections, there's going to be places for the minimum shaft diameter. So the first section up here is shaft diameters when torque and bending moment are present. So then we're going to input wherever we see blue. Okay. And then our minimum shaft diameter is going to be the last value at the bottom. Okay. And then you're going to notice that there's going to be, if you have another one for your shaft design, there's another chunk. And so there's, just kind of a random number of slots, if you would, that you could calculate those. Okay. Now, if you end up moving anything around on the spreadsheet, okay, if you end up moving anything around on the spreadsheet, you're going to have to kind of, move some other things around too, because it's referencing values from the first page. So for instance, modified endurance strength, we actually do this on sheet 1. And if you look up on the top here, it's looking to the cell on sheet 1 for that value. So if you move things around here, or if you add some in, you're going to have to go and check and make sure that it's looking at the right cell for that information. Same thing with the yield strength of the material. Okay, that's also looking to sheet 1 in a certain place. Okay. Then the next section, as we go down, you'll notice we have another kind of maroonish highlighted area. And this is going to be where we have shaft diameters with only torque present. So it looks a little bit different because there's different things to input for the torque only. And then it'll calculate its minimum shaft diameter for that particular place. There's a place in each one of these so that you can input the point. So if it's point A, left or right, point B, left or right, you can put those in and identify it. Then the next section is going to be our vertical shear only. And then the last section is going to be bending moments only. Okay, bending moments only. All right. Now, there is a third sheet here, and I called it summary of results. When you do your, I guess we're going to call them deliverables at the end, I'm going to have you use this, this place to summarize your results. What were the minimum shaft diameters? What were the actual shaft diameters after, you know, you applied basic sizes to them, and also how you're going to assemble, and you're going to kind of summarize things here. So we'll talk about what's going to go there, but there's that last tab. So this is how this spreadsheet is you know, kind of formatted right now. First sheet is going to be those inputs. Second sheet is going to be when we are going to actually do the minimum shaft diameters. But as you can see, you have to know where to go on the spreadsheet on sheet 2 to even know which one we're going to do. Okay. And that's going to be the pre-work that we're going to be working on leading up to this. Okay. All right. So that's the spreadsheet. Just coming back. Oopsie. Did I close my, there's my spreadsheet. I must have closed my my PowerPoint presentation, which maybe is not a big deal. Just want to get to the end of it. Okay. So so what we're going to do is we're going to open up our book to page 521, and we're going to start going over this example. So because you have already looked here, you probably have an idea of the process that we're going to be going through. Now, the spreadsheet is set up in a way that it's going to kind of follow along, but like I said, there are some things that we need to know. So the overview process here that I created in my handout is going to kind of walk us through what we need to do step by step. So the first step we've already talked about, have a layout of your shaft. Where are the gears, belts, bearing locations, retaining rings, all that kind of stuff. Making sure that you add the dimensions to the center lines or have the dimensions. And then also for how that shaft is going to be made and assembled. Okay. Then the next part here, we need to know the material. Okay, that's step number 1. And the problem gave us that material. It gave us, for this problem, SAE 1144 oil quenched and tempered 1000. Okay, now in order to find the information we need about this material, we're going to look to our Excel spreadsheet. Okay, so on sheet 1, right at the top, the first thing we're going to do is we're going to put in SAE 1144 oil, oopsie, 1144 oil quenched and tempered, and then that's just STL. Oil quenched and tempered, sorry, 1000 STL. Now, you'll notice right below there, they want to know what is the yield strength of that shaft material. Okay. Now in the book, they gave it to us, you know, not really gave it to us, but they told us we have to go to the appendix, but let's make sure that we know in the appendix where we can get this information, and that we get a number that they did. So they got 83,000, and we're going to go to the back of the book, the appendix, and find SAE 1144 oil quenched and tempered. So I'll go back underneath here. So in your book, go to appendix, I think it's appendix 3, appendix 2, appendix 3. And it's kind of where the materials all kind of start. Okay. On page 787, okay, you're going to find these are the design properties of carbon and alloy steels. Okay. So 787. Appendix 3, and here is the material designation going down the left-hand side. and we want to be an 1144. Okay, 1144.
Say 1144, oil quenching tempered 1000.
Right, yeah, and it's not. So this wouldn't be the table we look at, okay? So it's there, sometimes you might find what you need. You'll notice that you have these here, and there might be other ones where we can use the chart, but I would always start here. There is not an oil quenched and tempered 1000, okay? So we can't use this, all right? That's okay. So then what we're gonna do is we're gonna go over and we're gonna turn the page, and on page 789, here's another reference for heat treated materials. When something says oil quenched and tempered, it's heat treated, and the 1000 says I'm gonna go, it's to 1000 degrees. So down here, you're gonna notice that there are properties for heat treated, SAE 1144, oil quenched and tempered, okay? Now the temperature is gonna be to 1000 degrees Fahrenheit. So on the top scale right here, I'll point with my pencil. On the top scale right here, here's my 1000, okay? And that's gonna be 500, 600, 700. So this line right here is the 1000. Everybody see that? Okay. Now, to find my yield strength, I'm gonna go up, 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 and I'm going to hit that red line. And then we're gonna go over to the left, okay? Over to the left. Now, I'm gonna just kind of read what they got. They got a number of 83,000. So if we go over, I don't want to spend a whole lot of time trying to decipher exactly what that is, but you would take your time and you would figure out the scale, and they're seeing it as 83,000. Okay, that's where they would have gotten that from. Okay. So on our spreadsheet, that's what we're going to put in that spot, 83,000. And you can be doing this right along with me for this example. The next one is going to be the ultimate strength. We get that from the very same table, okay? Ultimate strength is the same as the tensile strength. It's always the highest point on that stress strain diagram, okay? So the stress strain diagram kind of goes up, right, at a high point, and then it kind of drops off when it actually ruptures. So on that highest point is the ultimate strength or tensile strength referred to. So on that very same chart, go back up, we're going to go 1000, 1000, 1000. We're going to go up to the tensile strength line, and we're going to go over, okay? And they're reading the tensile strength at 118,000, okay? 118,000. And that's what I'm going to be putting in again, just because, just so that our numbers align. If you would be reading this and you would say 120,000, 116,000, 115,000, reasonable numbers, okay? Reasonable numbers. The next one is going to be our endurance strength. This one, we actually have to travel to a different chapter. This is going to be on page 179, chapter 5, and we need to find the endurance strength. So you might want to put something in where the example is. So page 179 in our book. And what we're going to do is we're going to find our tensile strength, which was our ultimate strength, right? SU. Hold on. Oh, yeah. Customary units. I was going to say, what the heck? It's kips per square inch. I was like, K, why do we have K? It's kips per square inch here. So the top one is going to be US customary. And we are going to find the 118,000. This is the ultimate strength or the tensile strength. So here's 120, here's 15, and you're going to go up, 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 up. Now, you have to know the type of process that you're anticipating using to make this shaft. Most likely, it's going to have to be machined, right? So we're going to go up to the machined line, and we're going to go over and read our value, okay? Now, the book got, for endurance strength, 42,000, okay? So see if, you know, as you look at that, if that seems to make some sense. And it does. I think as you look at that, yeah, 42,000 seems reasonable. So we'll go to our spreadsheet, 42,000 PSI.
Work for any material.
Yeah, that's going to be steel. Yep. Mm-hmm. Then you're going to notice our next thing is going to be our reliability factor, CR. We're going to turn the page And at the top of page 181, there is a approximate reliability factor table. Okay, right here. Now the book, you get to pick what is your desired reliability. They picked 0.81 as their CR, so they wanted 99% reliable. So we're going to use that very same value again, 0.81. And then the size factor. This one's a little tough to estimate if you don't really know what size shafts you're going to have. If you're designing something as, you know, you're maybe going off of a current design and you're making some adjustments to it, you'll probably have an idea of what size the shafts are. But where we are at this point, you know what I mean? And we have just like case studies. It's hard to be like, this. So what the book did is they picked a value kind of in the middle-ish, and they picked a value, a size factor of 0.75. So if we go over and down, you're going to notice that the horizontal axis here has to do with the diameters that we're expecting this to be. So the larger the diameters, the lower this is going to be. The higher the diameters, the higher that value is going to be. That's really it. So 0.75 is where they landed, kind of looking and anticipating they're going to be around 4 inches in diameter. Okay. Now, if you're way off on that, you can always come back and adjust that after you do it. But we have other safety factors that are built in, and the stress concentrations that's pretty reasonable. So if you end up with 2-inch shafts and you did 4s, I don't think that's a big deal. But if you ended up with 1/2-inch shafts and you thought they were going to be 5 or 6, you might want to go back and do that adjustment. Okay. So 0.75 here. Now, once we get that 0.75 in place, it now has populated and calculated a modified endurance strength. Now, this modified endurance strength is going to be used in our stress calculations to determine the minimum shaft diameter. So if we go to sheet number 2, you're going to see some numbers now have populated in here. And these are the ones that they're pulling from sheet 1, which are the endurance strength, this modified endurance strength, and also the yield strength of the material. Okay, so those are the ones. So again, if you add some in here or you move things around, you're going to want to be cognizant of that so that you can make sure that they're pulling from the correct area when it's needing to. Okay, so that is our material portion. That's our material portion. So we'll continue to follow along back on our example here, and we'll also kind of look at where we're at on our procedure on our handout. The reason I have the handout is because I do, if you would, like I say, we deviate a little bit, and there's some things in here that you'll be adding that they don't do. So on our sheet here, our procedure, we're done with number 1, we're done with number 2. Now we're ready to determine what our torque is, okay, in the shaft. So we're going to input the horsepower and rotational speed in sheet 1, and we need to identify where it's acting. So we got to go back to our original problem statement to find this out. So as we look here, it says gear A receives 200 horsepower from gear P. So let's look at that arrangement. I'm going to turn my page because it's right here. So here is our shaft. So if we look in this direction, horizontally, I call that the x-axis. Vertically, that's going to be the y. And then the z is like coming in and out at us. Okay, so we're looking in this direction. From left to right, this is point A, then B, C, and D. So remember, B and D are going to be our bearings, and A and C are where we have our gears. It says here that A is getting its power to, did it say 200 horsepower? It says it's receives 200 horsepower from gear P. Gear P is not on our shaft. This is our input, okay? Everything is coming in on A, and then it's going to travel down the shaft, and it's going to leave on C. C then is going to be in engagement with Q. Q is not on our shaft. That's like the outside material or the outside machine, okay? So our torque is coming in on A. It's going to go across, and it's going to leave on C. Might as well say it now. Torque always comes in on center and leaves on center. All right. And that'll make a little bit more sense later. Okay. So here it's coming in. So if it's telling us that there's 200 horsepower coming in and our rotational speed of our shaft is 600, we now can go back to our spreadsheet, and down in the torques area on sheet 1, we can say, all right, 200 horsepower, 600 RPMs. And then we want to tell it where it's acting from. So in this case, not C to C, it's acting A to C. So you want to add that in as a, as a place marker. And here, these should be blank right now. I'm so sorry. I was practicing and making sure I knew what I was doing. So if you want to get rid of these guys, you can. The C's and the E's and all that. Okay. So in this case, we only have one, if you would, all of it's coming in on A and all of it is leaving on C. So in between is 21,000 pound-inches of torque that's going to be on our shaft. Okay. So that's all we need to do for that right now. Right. So let's go back to our procedure. Number 3, it says, okay, determine the torque. Now, the next thing we're going to do is we're going to determine the forces that are generated on the shaft due to the machine elements. Now, on this shaft, there's only 2 gears, so it's only gears that we're worrying about here. But on our second example, 12.2, we are going to have sprockets and shivs that are going to be there as well. So we're going to get a little taste of each one of them on that example, but we're going to keep it simple. And for our gears, we're going to do our tangential force and our radial force. Okay, our familiar ones. Okay, so let's first go to our spreadsheet and see what the spreadsheet needs. So we're going to go down a little bit. You're going to notice that there's some placeholders there for some more torque. We're not going to fill them in for this example, but if we did have some other ones that we need to do, we would add them there. So gear forces are next here. And we want to identify the gear location. This is going to be our gear A. Okay. And we're going to put in here, what is the transmitted torque on that gear? So we go back up here, it calculated to be 21,000. Okay. 21,000. Yeah. What is the pitch diameter of our gear? We've got to look at our example. So if we go back underneath, I'm going to look at this one. I think it's easier to see. A right here. Does it give it to us on this one? Maybe it doesn't. On the previous, I think it was that example too. So on page 511 at the bottom here, gear A is a 20-inch. That's going to be your pitch diameter. C is going to be 10, but A is our 20, and it's a 20-degree pressure angle. Okay. And that's what our spreadsheet is written for. So we're going to put our diameter in here as 20, and notice the units on the right-hand side are inches. Okay. And then our pressure angle is 20 degrees. So we've got our tangential and our radial force magnitudes calculated. Okay. Now, we might as well do gear C as long as we're here. Okay. So I'm going to put it in right away. And again, just because I know that the torque is the same, 21,000, and I just saw the diameter was 10 inches, 20-degree pressure angle. We've got our gear force magnitudes for each one of these now. Okay. So you should have tangential for A as 2100 and the radial at 764.31. And then for gear C, 4200 for the tangential, and then 1528.63 for the radial. Now is not a bad time. I always like to think of this in terms of whenever I talk about CAD. You want to save often, because you want to save whenever you feel like I don't want to redo what I just did. Okay. So now's a good time to do a quick file save as, save where you want this to go. Just gonna call this example 12 _1. And I'm gonna browse. I put everything on my desktop. I don't know about you. Okay. So you just want to have a place where you're going to be able to reference it if you need to, or if it goes away or whatever. Okay. So now I've got my gear forces here. Now, additionally, there's some more places for gears. You can ignore those. Those are just extra placeholders. And then down below, sprockets and V-belt shivs are down there too. Our problem doesn't have those in, so we can just leave those blank. Okay. Now we've got to look at how these gears generate or transmit their forces. So we're going to go back underneath here and we're going to review page 513. Okay, page 513. Now, at this point, I'm anticipating that you've got a good handle on tangential and radial forces. Your tangential force, remember, is going to be the force that's going to be perpendicular to the radius. And it's going to be the one responsible in gears for like shearing off it's the horizontal one here, shearing off that gear tooth, or it's the pitting stress. It's going to be where we have the pounding on the outside of the surface. Okay. But the other force that we have to take into consideration in shaft design, because it gets transmitted to the shaft, is going to be our radial force. Our radial force is always going to go from the point of contact and point back towards the center of rotation for the element that you're looking at. Okay. So because gear A is on our shaft, we've got to know from, in what orientation is its point of engagement. All right. Now, once we know that point of engagement, the other thing that we need to know is what is the direction of rotation of the shaft. Okay. So we're going to look at, let me see here. Okay. So the larger shaft here, and it's not really in our case, our points A and our points B, but in this case, we've got a gear that is considered what we call a driven gear, meaning it's getting its power from somewhere else. So this is a driven, and I'm going to underscore N, driven gear. A is a driven gear. It gets its power from P, coming in from probably a motor or something else, okay, wherever it's coming from. But A is dependent on its driver. So A is a driven gear. Okay, A is a driven gear. Now, that's important because when we know the direction of rotation, and we'll look at that in just a bit on our individual shaft, when we have a driven gear, that tangential force from its point of engagement is going to go in the direction of rotation perpendicular to the radius. So you'll notice here that my tangential force on this gear, which is a driven gear, is going in the direction of rotation. Do you guys see that? Okay. Driven is always easy. Always easy. Not that the other one's hard. But then my radial is going to go from that point of engagement down towards the center of that gear that we're analyzing. So it's going to point down. Okay. Now, if I'm a driver, C is a driver. C is going to take what it gets from A as it comes down the shaft, and it's going to send it out to Q. C is a driver. C, when it's a driver, even though the rotation goes in the same direction as the driven, it has to overcome the driven gear. So the tangential force points in the opposite direction of rotation, still perpendicular to the radius, but now it's going to go in the opposite direction of rotation, okay? Because it has to like push the other one along. So it's going to have that opposing force. Its radial will still go from the point of engagement back to its center of rotation, though. That's still the same. But we have to know that when it's a driver, the tangential points opposite the rotation. When I'm a driven, it goes in the same direction. Okay, that's all we have to know. A is, in our case, is a driven gear. So tangential is going to go in the same direction of rotation. C, on the other hand, is a driver. And so it's going to oppose, okay, the direction of rotation. If you need to reference that, it's here on page 513 in like a generic sense. But now let's look at it for our example. All right. On the top of page 522, right here, we have a pictorial of our shaft with the gears and engagement, as well as the bearing locations. We also have, looking down the shaft, gear A, and looking down the shaft, gear C. So these two right here are our shaft. And the direction they're looking in is looking down the x-axis in this direction. So this is a right side view of just gear A, and this is a right side view of just gear C. Okay? Right. So let's look at A first. We already said that A is a driven gear because it's getting its stuff from gear P. It told us that in the problem. So as we look down, they're showing us the direction of rotation for this shaft is going to be counterclockwise. Okay, so we find the point of engagement. The point of engagement is right here between P and A. Okay, so looking down the shaft, look at P is in front of it, right? That's where the point of engagement is. So number one, radial force is always going to go from that point of engagement and point towards the center of rotation of the element that we're analyzing. We're analyzing A. So from that point of engagement, that radial, you'll see here, is pointing to the right. I know it might not be easy on my illustration, but look in your book. Okay. Radial's done. Tangential is going to be perpendicular to that radial. I'm a driven gear. It's going to go in the direction of rotation. So since this is going counterclockwise, my tangential is going down in this view. All right. And that's going to translate directly to the center of that shaft. So what you're going to notice is right here, they're showing the tangential coming down, the radial pointing towards it. Does everybody see the correlation there? All right. Let's look at C now. Now, I should say those are directions. The magnitudes then are going to correlate to the values we got on the spreadsheet. And we'll see those come up in just a bit. But direction is like the big deal here. Now let's look at C. C is right here, okay? C is on our shaft. It is rotating counterclockwise. And on the back side of it is where its engagement with Q is. That's going out to the machine, whatever it is. Now, its point of engagement, when we look here, down the shaft, down the x-axis, here's our shaft. On the back side, on the right, is going to be its point of engagement. The radial will go from that point of engagement and point towards the center of the shaft. So in this case, pointing to the left. Okay, that's the WCR. The radial force at C. The tangential, because this is a driver, this is going in a counterclockwise direction. It would go up. It's going to be in the opposite direction of rotation because remember, it has to like push itself out, you know, and it has to overcome the inertia of the other gear that doesn't want to turn. Okay.
So in this case, which direction the arrow is pointing down?
Yep, it's pointing down. Yep, because it's opposite the direction of rotation because it's a driver. Because it's a driver, not driven. Okay. And then you're going to see here that it translates up here as well. Now, here's your challenge. Here's your challenge. And they did it wrong in the book. So I'll show you how it's different and we'll go through it together. We now want to put this in 2D form. Okay. We need to draw the free body diagrams of both orientations because we have two forces that are 90 degrees to each other. We need to look at this in a traditional front view. In this orientation right here, this would be our front. Okay. And then we also need to look down on the top of it as a top view. And then we're going to add also a right side view. All right. We're going to add a right side view. So over on the next page, at the top of the next page, they did this one okay. Their front view is okay. This one, they did up from the bottom and we'll look at it. We're going to get the same numbers. Our directions are going to be exactly opposite, but it's okay because we're going to do a front and a top. That just makes sense. It doesn't make sense to do bottom. So when we compare here, we're going to notice a difference. Now, before we can get our shear and moment diagrams, we have to have then the reactions at the supports calculated, right? So we would have to do all of our statics. We would have to lay this out. We do the reactions at the supports, and then we would get to do our shear and moment diagrams. Remember how fun that was by hand? You guys got to do it by hand. You don't have to do it by hand. That's what we have MD solids for. That's what we're going to look at next. So this is a great, I've been talking for about an hour now. So I think this is a great, let's take a little break, kind of a little bit of respite from this. And then when we come back, we're going to look at sketching these out. okay, by hand first, because I want to make sure that you understand where the directions come from. We're not just going to copy what's here. We want to understand where they're coming from. And then we're going to learn how to use MD solids to lay this out here to calculate our reaction to the supports, as well as the shear and moment diagrams are going to be done for us as well. Okay, so I'm going to stop our recording here. We're going to take a 10-minute break and we will be back. Oopsie.